In order to understand what exactly containers are, it makes a lot of sense to compare them to two of their precursors, that is, bare metal and virtual machines. So let's first start by understanding what the term bare metal refers to. This is a machine that is hardware infrastructure with an operating system on top of it. When you deploy an app on bare metal, your app is going to directly interact with the operating system and the infrastructure of that particular machine. A great downside of bare metal is that your app is not likely to be very portable. Think back to developing on Windows or in the Microsoft ecosystem maybe 20 years ago, and think about how painful it was to port those applications over to different platforms. In order to reduce this burden, virtual machines came into being. A virtual machine typically has the following setup. There is the underlying hardware or the infrastructure. Above this is a host OS, this is optional, and above this is a hypervisor. The hypervisor is effectively a level of abstraction which will shield everything running above it from the underlying host OS and the hardware. You should know, by the way, that there are two types of hypervisors, and one of those types does not require an underlying host OS. So here the hypervisor plus the host OS might sometimes be combined into one entity. In any case, the important point about virtual machines is that each one of them runs on top of this hypervisor. So each virtual machine is going to contain its own guest OS, and above this guest OS will reside our applications. So when you're writing apps for virtual machines or to be deployed on virtual machines, you write them inside this virtual machine abstraction, which has a guest OS. That guest OS interacts with the hypervisor, which in turn interacts with the underlying infrastructure. Virtual machines and companies which make them, such as VMware, have had a great deal of success in the last 15 odd years. One downside of virtual machines is that these individual abstractions are still quite heavyweight. Why are they heavyweight? Well, because they contain an operating system, the guest operating system. In the world of cloud computing, this great heavyweight nature of virtual machines can be a bit of a disadvantage when it comes to features like auto scaling or auto healing. Another drawback of virtual machines is that portability is still not all that great. If you have experimented with migrating a VM from an on-premise data center to any one of the leading cloud platforms, you probably have experienced the pains of VM migration. So working with virtual machines certainly buys us some abstraction and some portability, but not a whole lot. The next item in the evolution of compute options is, of course, containerization. The Docker website defines a container image as a lightweight standalone executable package of a piece of software that includes everything needed to run it: the code, runtime, system tools, system libraries, and settings. Well, that's the definition of a container image. It's best understood using an analogy. Think of a container image as something akin to a jar. In Java, in the days before Java programming, if you wrote, say, Visual C++ on a Windows machine, you were tied to the world of Windows and of Microsoft's Visual Studio. Once Java came into existence, there was now a layer of indirection. You could now develop your code in Java. This would be platform independent. This code could then be compiled into jars. Those jars are analogous to containers, such as Docker containers, and those jars could then be shipped in order to run on a different machine. The platform independence came because of an additional level of indirection. In the case of Java, that additional level of indirection was the Java runtime. In the case of containers, that is a container abstraction layer such as Docker. Docker acts as a level of abstraction between your container images and the underlying hardware and infrastructure, and it effectively maps any system dependent calls that your application makes. The great upshot of containerizing your workloads is that your executable units no longer need to lug around their operating system with them. In contrast to virtual machines, containers are a lot more lightweight. Where a virtual machine would be in order of gigabytes in size, containers are likely to be in order of megabytes, that is several orders of magnitude smaller. This also means that in a cloud-driven world where we care about speed of auto-scaling, containers are likely to scale up faster. And lastly, containers are ideal for a world in which we have both an on-premise data center and one or more public clouds. This is called a hybrid model. So if we are developing on a data center on-premise and also planning to move those computing units to different public cloud providers, containers are very likely going to be our preferred compute option.